This is my intermediate algebra course. Today we're going to prepare for the fourth test of the course. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In previous parts of the course, I mentioned that there are some subjects where you can study an hour the night before and get a really good score on the test. Well, math doesn't work that way. With math, you need at least 2 days to prepare for an exam, and really you need 3 or 4 days minimum if you want to get a really good score. But it doesn't matter how many times you tell students to study for a test, they're not going to do it. So in order to force you to do at least some studying for the test, we're going to do a practice test right now together, and I'm going to give you a practice test for homework. And these tests are not only going to force you to do at least some studying, but they're going to familiarize you with the format of the test so you can't say that you were caught off guard. And be aware that these practice tests are not going to guarantee that you'll get a really high score, but hopefully they'll at least ensure that you pass the test. If you want to get a really high score, you need to go back and do every single variation of every problem that we did. These practice tests are going to be fairly representative of the problems that we've done, but they're not going to have every single variation. So that said, let's start the test. You can use a calculator, but only for simple calculations. Now, as usual, I want you to try these problems on your own. Don't just watch me do them. See if you can do these problems on your own. And if you get stuck, that's okay, but attempt problem number 1 on your own and see if you can do it. And when you come back, we'll do it together. Okay, we're back. So let's write the parent relation. This is the square root parent relation, and the parent equation is y is equal to square root x, and the parent graph, of course, looks like this. You should be very familiar with the parent graph, but we're going to move it 1 unit to the right and 2 units up. So 1 unit to the right, 2 units up, and there you go. Okay, so if you got that one right, good job. Go ahead and try number 2, and when you come back, we'll do it together. Alright, we're back. This is the absolute value parent relation, and the parent equation is y is equal to the absolute value of x. So that graph looks something like this. It's a V, but we have a negative on the x, which means that we're going to reflect across the y-axis. So we're going to flip over the graph. Each point is going to go directly across. So if there's 1, 2, 3, 4 units from the y-axis to that point, then you go exactly 4 units to the other side. But when you do that, you just get the same graph. So reflecting across the y-axis doesn't really change the way that this graph looks. So if you got that graph, good job. Okay, go ahead and try number 3. When you come back, we'll do it together. Alright, we're back. The parent relation is the exponential relation, and the parent equation is y is equal to 3 to the x. And what kind of dilation is this? Well, we're dividing so it's going to be a stretch, and we're dividing y, so it's going to be a vertical stretch. And so the asymptote is going to be on the x-axis. The dilation is not really going to change the location. Remember, sometimes dilation does change the location of an asymptote, but when the asymptote is on the x or y axis, it does not change the location. So normally, if we plug in 0 to our parent equation, 0 for x, then the y value would be 1. But now we're dividing y by 2, so that means we're going to multiply all the y values by 2. So we're going to move that up. Also, if you plugged in 1 to the parent equation, you would get 3. So we're just going to take those points and we're going to double the y values. And that's our graph. If we plug in -1, we get 2/3. But I don't really require you to be that exact when you go to the left part, the part on the left side of the y-axis. And let's not forget to write our asymptote equation. The asymptote is y is equal to 0. So if you got that right, good job. Go ahead and try number 4, and when you come back, we'll do it together. Okay, we're back. The parent relation is the reciprocal relation, and the parent equation is y is equal to 1 over x, and our asymptotes are going to be on the y-axis and the x-axis, but then we add 1 to x and add 1 to y, which means that we have to move the asymptotes 1 unit to the left and 1 unit up. So that means that the new intersection point is going to be at, whoops, we're not going to move it up, we're going to move it down. I think I said up, I meant down. 1 unit to the left and 1 unit down. There we go, so there's our new intersection point at -1, -1. And we should have our 6 points memorized. Those are the 6 points. If we assume that, or pretend that this is the origin, then we go out 1 to the left and down 1, and 2 to the left and down 1/2, 1/2 to the left and down 2, and over here we go to the right 1 and up 1, and so on and so forth. It's the same 6 reference points that we always graph. So the asymptote equations are the equations of those dotted lines. X is equal to -1 and y is equal to -1. So if you got those answers, excellent. Good job. Alright, so now let's try number 5. See if you can do number 5, and when you come back, we'll try it together. Okay, we're back. So we have a negative in front of x cubed. The transformation properties don't tell us what to do in that situation, so I have to multiply both sides of the equation by -1. And now the transformation properties will tell us what to do. We know what to do when there's a negative on y, but we don't know what to do when there's a negative on x cubed. So the parent relation is obviously y is equal to x cubed. And if we graph that, we have 0, 0, 1, 1, negative 1, negative 1, 2, 8. But that's off the window. And if we have a negative on the y, then that's going to reflect across the x-axis. So our new graph is going to look like this. So that's the graph of negative y is equal to x cubed. So if you got that right, good job. Okay, try number 6, and when you come back, we'll do it together. All right, we're back. So we're subtracting 1 not from x. We're not subtracting 1 from x. We're subtracting 1 from negative log base 3 of x. And we don't have a negative on the x. We have a negative on log base 3 of x. So we don't know what to do to graph this equation. But if we add 1 to both sides, we get y plus 1 is equal to negative log base 3 of x. Well, now we can see we're just adding 1 to y. So we're on the right track. If we divide both sides by negative 1, or multiply both sides by negative 1, then we get the following equation. And if we write the negative on y first and then add 1, we can see how to graph this. So we didn't really need quite this much space here. We can write the altered form down here. And by the way, we could distribute this negative 1. You can do that if you want. But just be aware that the steps necessary when we transform the parent relation are going to be different. So we need to graph this relation. The parent relation is obviously y is equal to log base 3 of x. There's always a vertical asymptote when dealing with the parent logarithmic relation. And remember, if you plug in 1 to a logarithm, you always get 0, and if you plug in a number that's the same as the base, in this case 3, you always get 1. So 1, 2, 3, 1, 2, 3, and then 1. And those are the only points we really need to graph this relation. But now we're going to write a negative on the y, or we're going to replace y with negative y. And the reason we're going to do that is because we wrote the left side of the equation in this form. We can't add 1 and then write a negative on y plus 1 because the transformations don't tell us what to do in that situation. The transformation properties tell us what to do when we write a negative on y, but they don't tell us what to do when we write a negative on y plus 1. So what that tells us to do is reflect across the x-axis. So we're going to flip the graph across the x-axis. And then we're going to add 1 to y. So this equation is exactly the same as this equation. The only difference is we added 1 to y. So what that means is we're going to move the graph down 1 unit. So we have the following curve. And there you go. So if you got that one right, good job. Make sure that you write the equations, the green equations here. Alright, so on to number 7. Go ahead and attempt number 7. When you come back, we'll do it together. Alright, we're back. So we need to use the vertical line test. What we do is we draw vertical lines, and if these vertical lines only touch the graph once, then that means that the graph can be a function. But if any of these lines touch the red graph more than once, that means the graph cannot represent a function. So in the second graph, if we draw the line, we touch twice at certain parts, so this graph cannot represent a function. And here we have the same situation. These lines are touching the red graph in more than one place, so that cannot be a function. And this next problem is kind of tricky, because it looks like our line is going to touch twice here, but it actually doesn't, because this is an open hole here and a closed hole, so it only touches once. In every other place, the vertical lines touch once. So that means that that can be a function. So if you got that right, good job. Okay, try number 8. When you come back, we'll do it together. Alright, we're back. So let's find f of negative 3. We just plug in negative 3 to that expression up there. The absolute value of negative 3 is 3. And by the way, I'm getting this negative 3 from here. These green numbers are the inputs of a function, and the orange numbers are the outputs. We're looking for the outputs. 3 divided by 3 is 1, and then 1 plus 5 is 6. So now let's plug in, and let's go ahead and enter that in. That's 6 there. Now let's plug in 0 to the function. The absolute value of 0 is 0. And 0 divided by 3 is 0. And 0 plus 5 is 5. So we can enter 5 in the table. And now let's plug in pi. Again, I'm getting pi from the table up here. We have the absolute value of pi divided by 3 plus 5. The absolute value of pi is just pi. And we can leave our answer like that. You could use a calculator if you wanted to, but I'm not going to make you do that. So we can enter pi over 3 plus 5 in our table if we have room. Now we're going to plug in 6. So we have the absolute value of 6 over 3 plus 5. Absolute value of 6 is 6. 6 divided by 3 is 2. 2 plus 5 is 7. You don't have to show all these steps, but you do have to show some work. So if you got that right, good job. Go ahead and try number 9, and when you come back, we'll do it together. Okay, we're back. So this is kind of a trick problem. They want us to plug in -1 into this function, but we have two equations. We have this equation and this equation. Which one do we use? Well, when x is between 10 and 0, we use the purple equation. When x is between 10 and 20, or equal to 10, then we use this equation. F of x is equal to 3, that is. And the top equation is x plus 1 is equal to f of x. But -1 is not in any of these intervals. So what that means is the answer is undefined. So that was kind of a trick problem. So now we're going to plug in 8. 8 is in this interval. 8 is between 0 and 10. So that means we're going to use this equation here, x plus 1. So 8 plus 1 is equal to 9, and there you go. So now we're going to try to plug in 10. And notice that when x is between 10 and 20, or equal to 10, we use this equation. So that means when x is equal to 10, or between 10 and 20, the output, the y value, is always going to be 3. So the answer is just 3. If you had f of 11, f of 12, f of 15, f of 19, f of 19.9999, the answer would always be 3. So now we're going to plug in 36, but again, this is a trick question because 36 is not in any of these intervals, which means that the answer is undefined. So if you got those right, good job. Okay, go ahead and try number 10, and when you come back, we'll do it together. Okay, we're back. So f plus g of x is just notation that means f of x plus g of x. And we know f of x is x squared, and we know g of x is 1 over x, so you're done. That's it. So it's pretty easy. F of -2, or f over g of -2, what that means is f of -2 over g of -2. So f of -2 is -2 squared, and g of -2 is 1 over -2. So just to be clear, f of -2 is that, and g of -2 is that. So -2 squared is 4. And if you do the math, we end up with -8. When you're dividing by a fraction, you flip the fraction so it becomes 2. And you multiply, so 4 times -2 is -8. If you got that right, good job. Okay, go ahead and try number 11. When you come back, we'll do it together. All right, we're back. So remember, when you're trying to find all the possible x values of a function that will produce an output, it's sometimes easier to think about what x cannot be, what the inputs cannot be. If you plug in a number that gives you 0 in the denominator of a fraction, that means that 1 over 0 is undefined. So if you plug in that x value, it won't give you a y value. Or if you think about it in terms of inputs and outputs, if you put that input into your function, it won't produce an output. So what that means is x plus 2 cannot be 0. Subtract 2 from both sides, we see that x cannot be -2, because if you plug that in there, you get 0 in the denominator. This is just a way to show your work. So the domain is all real numbers. And remember, it's important to say all real numbers. All real numbers except -2. So if you got that right, excellent. Okay, go ahead and try number 12, and when you come back, we'll do it together. All right, we're back. So remember, it's often easier to think about what the inputs cannot be. And when you have a square root, remember, the inside part of the square root cannot be negative. So that means that x over 2 plus 1 has to be greater than or equal to 0. Greater than or equal to 0. So now if we solve this inequality, we can see what x must be. If we subtract 1 from both sides and multiply both sides by 2, we see that x must be greater than or equal to -2. Now be aware that if you multiplied both sides by a negative, you'd have to flip that inequality, so don't get that wrong on the test. If you multiply or divide both sides of an inequality by a negative, you have to flip the inequality. We didn't have to do that here, but you might have to do that on the actual test, so be aware of that, or the practice test for homework. So it says to write the domain in interval notation, so be careful about that. If you write the domain in the wrong notation, then you're going to lose a lot of points. So in interval notation, we say the domain is all numbers between -2 and infinity, and it's greater than or equal to, so we have to write a bracket, which means that it can be equal to, the inputs can be equal to -2 or greater than -2. So if you got that one right, good job. Okay, go ahead and try number 13. When you come back, we'll do it together. All right, we're back. So the domain of this function is all the x values of the points on this graph. And it says to use set notation. Don't write in word form or interval notation, or else you're going to lose points. We want the answer in set notation. So you're going to write braces, the set of all x values such that x is between -5 and 2, but also equal to 2. So we state what variable we're using, and then we state the restriction on that variable. All x values such that x is between -5 and +2, including 2. Now the range is all the y values of the points on this graph. But notice that there's only one y value that's represented. The set of all y values such that y must be equal to -1. Because all the points on this graph have y values that are equal to -1. So again, you state the variable that you're using and the restriction on that variable. So if you got that one right, good job. Try number 14, and when you come back, we'll do it together. All right, we're back. So there's two parts to this problem. Part number 1, we're going to find A using this formula. We know P is 5. That's this number over here. It's the distance from the vertex of the dish to the receiver of the dish. The receiver is this thing here. And we're going to use that information to find A. So if we multiply both sides of the equation by 4a, we get 20a is equal to 1. Divide both sides by 20 and we get a is equal to 1 over 20. And then we move on to part 2 of the problem. Let's write our vertex form of a parabola, because that's what this dish is. It's in the shape of a parabola. And let's draw some axes over here so we can kind of get an understanding of what we're doing. We're going to make the vertex of the parabola 0, 0. And this point over here will make, that'll be 4y. Now, why is it 4? Well, because that's half of 8. We know this whole distance here is 8. They told us that up there. So from the vertex to that point, it's going to be a total of 4 horizontal units. And we're looking for y. I should put these coordinates a little higher there. So let's fill in. Y is going to be, well, we don't know. A, we found, is 1 over 20. That's this number up here. And x, the x value is going to be 4 at this point. We're going to use this point to find that y value. We want to know how deep the dish is. That's going to be this yellow distance here. That's how deep the dish is going to be, or how long it is. So I have 4 minus the x value of the vertex. The x value of the vertex is 0, and the y value of the vertex is 0. So if we do the math, we can find y, and once we find y, we'll be done. So we have y is equal to 1 over 20 times 16, which is 16 over 20, which is 4 over 5, and the units are meters. You can write lowercase m for meter, or you can spell it out. So if you got that one right, good job. Okay, go ahead and try number 15, and when you come back, we'll do it together. All right, we're back. So the amount of money in a bank account is equal to the amount that you put in times e to the RT power, where R is the interest rate, annual interest rate, written as a decimal, and T is the number of years. So we're told that after a certain amount of time, there's $140,100 in the bank account, and the principal, the amount that you deposited, is $97,000, and the interest rate is 0.02, and we're looking for the time that the investment was in the account, or whatever the investment, wherever it was invested. So now we're going to divide both sides of the equation by 97,000. And don't be afraid to use your calculator. So dividing by 97,000, we get 1.4443299. And then we're going to, well, we can't do anything, we're stuck. unless we understand how to convert between an exponential equation and a logarithmic equation. We need to know how to tell our calculator what to do, because this is a calculator problem, obviously. And remember, e is just a constant. So we need to tell the calculator we're looking for the exponent when e is raised to that exponent. We get this number, and so that's going to be log base e of 1.4443299. But remember, our calculator doesn't use that notation. It uses ln. Whenever you have log base e, it's always written as ln. And then, of course, we're going to divide both sides of that equation by 0.02. And maybe we should do that later. So I'm going to enter that number. You should have that number in your calculator. If you don't have it still in your calculator, you can just enter that and then push the ln button. If you're using a graphing calculator, you have to press the ln button first, then enter this number. And we get 0.02t is approximately equal to, and by the way, this should be approximately equal to also, if you want to be exact, those two steps. So now we get 0.3676 45, and we're going to divide both sides by 0.02. So t is approximately equal to 18.382, and this problem doesn't tell us what to round off to, so we can just leave it. And that's the number of years that our money was in the account. So if we got that one right, good. All right, on to number 16. Try number 16. When you come back, we'll do it together. Okay, we're back. So the amount of money in an account is equal to the original amount that you invested times 1 plus the interest rate written in decimal form divided by the number of times you're compounding per year to the number of times you're compounding per year times the amount of time in years that the money's in the account. So the principal, the amount you invest, is $8,000, and the rate is 0.05 in decimal form, and it's compounded per month, so that's 12 times per year. Remember, n is always number of compounding events per year, and that's 12. That's n up there also, times the time, which is 4 years that the money's in the account. And now we just have to simplify that expression. You might wonder if you can just enter this whole thing into your calculator. I'd prefer if you actually show some steps. So 0.05 divided by 12, that's going to be kind of a weird number. Then 12 times 4 is 48. And then we're going to add 1 in the base there. So we have 8,000 times 1.00416 bar to the 48th power. So again, it's going to be different if you're using a graphing calculator or a scientific calculator, but with my iPhone, I have that number in my calculator, and I'm going to press the X to the Y button, and then 48 and I get 8,000 times 1.22089.5. And if I multiply that by 8,000, this is going to be our final answer, so $9,767.16. Make sure that you round off to the nearest cent. The problem doesn't tell us what to round off to, but when you're dealing with dollars, obviously you can't have a fraction of a cent. At least not in most cases. Okay, so if you got that one right, excellent. So on to number 17. See if you can do number 17. When you come back, we'll try it together. All right, we're back. So we need to isolate the exponential expression, which means we need to move the 6 and the -4 to the other side of the equation. So I'm going to subtract 6 from both sides. And then I'm going to divide both sides by -4. And at this point, we're stuck. We don't know what to do. Obviously, we're going to have to use the calculator because that e represents 2.71 something 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 to the x power is equal to 6. That's going to require a calculator for us to solve that. So what do we tell the calculator? Well, we tell the calculator log base e of 6, but this is a special case where you have base e, so we're going to press that button ln. So ln 6 is equal to approximately 1.79, and it says round to the nearest thousandth, so 792. If you got that one right, perfect. Okay. Try number 18. When you come back, we'll do it together. All right, we're back. So we're going to use logarithm property 7 to raise this 5 up to the exponent. And you know what, before we do that, let's go ahead and recognize that we don't have any bases written here, which means base 10, right? So let's recognize that we have base 10 logarithms. And now let's use logarithm property 7 to raise that 5 up. So now we have log base 10 of 32. And now we're going to use logarithm property 6 because we're subtracting logarithms, so we can combine those logarithms into 1. And now we're stuck. We can't go any further unless we recognize how to convert from a logarithmic equation to an exponential equation. Remember, the base is always this small number here. The exponent is always what the logarithm is equal to. And whatever's inside the log function goes on the other side of the equation. Again, this is just all definition. So 10 to the first power is just 10. Multiply both sides by x, and we get 10x is equal to 32. And let's see if we can get some more room here. Divide both sides by 10, and we get x is equal to 3.2. So if we got that one right, good. Okay, try number 19, and when you come back, we'll do it together. All right, we're back. So the magnitude of an earthquake is defined to be log base 10 of 1,000 times the length of a disturbance on a seismograph in millimeters. And let's write the base. The base is not written because you don't have to write the base, but let's just make sure we know what that is. It's base 10. The notation doesn't show a 10, but we know it's 10. And now we have log base 10 of 1,000 times 0.8. 1,000 times 0.8 is 800, and log base 10 of 800 is 2.9. So approximately equal to 2.9. That's good enough. It doesn't tell us what to round off to. So that is the magnitude of that earthquake. If you got that one right, good job. Okay, go ahead and try number 20, and when you come back, we'll do it together. Okay, we're back. Write the domain of the function in set notation. So we need to write the domain of that function, but you can see that, well, the domain is going to be pretty easy. You don't really need to graph this function in order to see the domain. We don't have any square roots. We don't have fractions with variables in the denominator, and we don't have any logarithms. So there really are no restrictions for the domain. In set notation, we say the domain is the set of all x values such that, actually we don't even need that. We can just say, remember when you have, when your answer is all real numbers, in set notation we just say all real numbers. Set notation doesn't really apply in that situation. So now we have to write the range of the function, but that's not as easy to do. We can plug in any inputs and we're going to get an output. Again, because there's no roots or logarithms or there's no fractions with variables in the denominator. But there might be some restrictions on the range. We don't know what all the outputs are going to be, so in order to help us do this, let's graph the function, but it's a very complicated function. So we're going to graph using transformations. Let's draw the parent, whoops, that should be a square, the parent function. The parent function looks like this. And if you forget those reference points, that's okay because you can use the equation. And then we're going to, well, it looks like we're going to have to change the form of this equation so we know what's happening here. So I'm going to switch f of x to y. It just makes it easier for us to work with the equation. Then I'm going to subtract 2 from both sides of the equation, and now you can see that we're actually subtracting 2 from y, which means that we're taking the parent equation. It's eventually going to be moved down. Then we're going to divide both sides by 3. Both sides of the equation, and now we can see what to do. Whereas before we didn't really know. The transformation properties didn't tell us what to do when you're adding 2 to all this stuff, or multiplying 3 into this stuff. But now we can see we're subtracting 2 from y, and before that we're dividing y by 3, and so on and so forth. So we need to be careful about the order in which we do this. If we subtract 2 first and then divide by 3, well, the transformation properties don't tell us what to do when we're dividing y minus 2 by 3. So that doesn't work. So first let's divide y by 3. So that's going to multiply all the y values by 3. So that's going to be a vertical stretch. We're pulling the graph upwards. It's one way to think about it. So then we're going to translate. So we're going to subtract 2 from y, or we're going to replace y with y minus 2, and we're going to replace x with x plus 1. So that's going to move the curve 1 unit to the left and 2 units up. So then we get this graph here. And then we're going to replace x with negative x. So that means that we are going to reflect across the y-axis. And that gives us the following graph. So how does that help us find the range? Well, we can see all the points, or all the y values of the points on this graph represent the range, but the y values never go below 2. They're all above 2. So the range in interval notation, make sure you write interval notation, is 2, anything 2 or greater. So if you got that right, good job. Now, you don't have to graph if you don't want to, but that's really the best way to figure out what the range is going to be. And you can see that we can figure out the domain also. The domain is all the x values of the points on this graph, but the x values don't have any restrictions. You're going to go out to infinity this way and infinity this way. The higher the graph progresses. So if you got that one right, good job. Okay, so go ahead and try number 22. And as soon as you find a pathway that works, you can use that pathway. You don't have to check every single pathway. So try number 22. When you come back, we'll do it together. Okay, we're back. So we're going to graph this equation, but we want to use the transformation properties to graph the equation. And in order to use those properties, we have to make sure that we can use them in a way such that we don't have to modify the expressions, change the form. So we're starting with the correct parent equation. We're subtracting 2 from y and adding 3 to x. That's okay. We can just move 2 up and 3 to the left. But here's the problem. We're multiplying y minus 2 by 3. The transformation properties don't tell us what to do in that situation. There's nothing wrong with the equation. The equation is fine. We get to the right equation, but the problem is if we multiply y minus 2 by 3, the transformation properties just don't tell us what to do in that situation. So there's nothing wrong with it. It's just we can't use the transformation properties. The same is true. These two steps are fine, but now we're putting a negative on y minus 2. if we write a negative on y alone, that tells us to reflect across the x-axis, but we're not doing that. We're putting a negative on y minus 2. The transformation properties don't tell us what to do in that situation. Whoops, that should be an x. So again, there's nothing wrong with the equation. We're building the correct equation. It's just we can't use that pathway with the transformation properties the way that they're written. So we're starting with the correct parent equation, then we're multiplying y by 3. That's fine. That just tells us to divide all the y values by 3. Then we're replacing y with negative y. Well, that tells us to reflect across the x-axis. So the transformation properties we're gonna be able to use those transformation properties so far. Then we're replacing y with y minus 2 and x with x plus 3. Now be aware that when you multiply 3 by negative y, you get negative 3y. So don't be confused by that. So that pathway is going to work, because if you replace y with y minus 2 and x with x plus 3, you just move the graph 2 units up and 3 units to the left. So we can use pathway number 3 to help us graph so let's first graph the parent relation. So we did this once today. This is just the V shape, very easy to graph. And again, we have to choose our pathway number 3. So then we're going to dilate. I'm following this pathway. That means we're going to divide all the y values by 3. And we're going to get this graph here. And the V, the sides of the V are lines. So once we figure out the slope, up 1 and over 3, we can use that same slope to find the other points. And so we dilated that graph. And then we're going to replace y with negative y. That's this step up here. So then we get negative 3y is equal to the absolute value of x. So we're going to reflect across the x-axis. And we get the following graph. Because we replaced y with negative y, we're reflecting across the x-axis. And then we're going to replace y with y minus 2 and x with x plus 3. And that takes the previous graph and moves it 2 units up and 3 units to the left. And again, we can use the same rise and run to find all these points. So down 1 over 3, down 1 over 3, down 1 over 3. It's kind of hard to draw a straight line sometimes, but just try your best. Okay, so that is the graph. If you got that right, good job. This is the final graph. If your graph doesn't look like this, that means you did something wrong. Now, if you chose a different pathway, we didn't check these, so I don't know if one would actually work, but you may choose a different pathway, but it should get to the same point. They're the same graph. Okay, go ahead and try number 23. Be aware that this problem wants you to graph the parent relation of this equation. So be sure to follow directions properly. Try number 23. When you come back, we'll do it together. Okay, we're back. The parent relation is the reciprocal relation, and the parent equation is y is equal to 1 over x. So we're going to graph this equation, not this equation. So again, be sure that you follow directions. So the reciprocal relation, we already graphed that once today. The parent relation, the parent graph looks like that. And of course we have our 6 reference points, 1, 1, 1 half, 2, 2, 1 half, negative 1, negative 1, negative 2, negative 1 half, and negative 1 half, negative 2. It's the same 6 reference points that we've been graphing for quite some time. So there you go. If you got that one right, good job. So go ahead and try number 24. In 24, you're going to graph this equation using transformations. Starting from the parent graph, you're going to transform step by step, just like we did in previous classes. So go ahead and try number 24. When you come back, we'll do it together. Okay, we're back. We can't really do anything with this equation because we don't really know what to do in its current form. So I'm going to add 2 to both sides of the equation. And I'm going to divide both sides by negative 2. Or I can multiply both sides by negative 1 half. I'll get the same thing. And just to help us see what's happening here, I'm going to take that negative and write it up in the numerator of the fraction. So we have negative y plus 2 over 2 is equal to 1 over x minus 2. And that's going to help us graph. So we're going to start again with the parent graph, and we need to figure out what steps to perform. We need to either write a negative on y or divide y by 2 first. We cannot subtract 2 from x and add 2 to y. Well, technically we could subtract 2 from x. That wouldn't make a difference. But adding 2 to y, we can't do that because if we write a negative on y plus 2, the transformation properties don't tell us what to do in that situation. And if we divide y plus 2 by 2, again, the transformation properties don't tell us what to do. So we need to add 2 to y in the last step. So I'm going to start off by writing a negative on y. That doesn't change the location of the asymptotes. But it reflects all the points across the x-axis. So now my points look like so. And then I'm going to divide y by 2. So we have negative y over 2 is equal to 1 over x. So I'm multiplying all the y values by 2. So we have negative 1, 2, negative 1 half, 4, negative 2, negative 1, or negative 2, positive 1 that is. And 1, negative 2, 1 half, negative 4, and positive 2, negative 1. So I'm going to connect the dots. So again, we stretched vertically. And that does not change the position of the asymptotes because the asymptotes are on the axes. But again, just be aware that you may get a problem where your asymptotes are not on the axes, and if you dilate, you have to change the position of the asymptotes. You have to divide by 2 or multiply by 2 or whatever it may be. So now we're going to replace y with y plus 2 and x with x minus 2. So we have negative y plus 2 and x minus 2. And if you write this negative next to the fraction symbol, you don't have to use parentheses. But if you write it up in the numerator, you must use parentheses unless you want to use the distribution property. So just be aware of that. This equation is the same as this equation. The only difference is, in this equation up here, the negative is in the numerator, whereas down here the negative is just in front of the fraction. So you can write it however you want to write it. So what that means is we're going to move the entire graph 2 units to the left, or actually 2 units to the right and 2 units down. And our points are going to be in the same relative positions. Connect the dots. And there you go. So that is the graph of that equation. So if you got that right, good job. Okay. So now on to the last problem. George has quarters, nickels, and dimes in his pocket, 30 coins in total. The number of quarters is 1 more than the number of dimes. How many of each type of coin does he have if the total value of the coins is $4.20? Try number 25, and when you come back, we'll do it together. All right, we're back. We're going to let Q be the number of quarters. Remember, you must define your variables. N is going to be the number of nickels. And D is going to be the number of dimes. Okay, so we know that the number of quarters plus the number of nickels plus the number of dimes is equal to 30. How do we know that? Well, because it says that in green up there. We also know that the number of quarters is 1 more than the number of dimes. How do we know that? Because it says up there. We know that 0.25 times the number of quarters plus 0.05 times the number of nickels plus 0.1 times the number of dimes is equal to 4.20. How do we know that? Because the total value of all the coins is equal to $4.20. So that's a system of equations. I'm going to use a brace there to connect those. And we're going to use substitution because Q is solved for. That means we're going to rewrite the first equation, but instead of Q, we're going to write what the second equation tells us that Q is equal to. Then we're going to take the third equation and do the exact same thing. And maybe I'll put that over here. I'm going to rewrite the purple equation. I'm going to write the exact same equation, except instead of Q, I'm going to write what the second equation tells us that Q is equal to. this over a little bit. So now we're just going to simplify these equations. So I'll start over here. So we have d plus d is 2d. And if I subtract 1 from both sides, we get 2d plus n is equal to 29. So we simplified that equation. And over here I'm going to distribute. So we get 0.25 plus 0.25d and we can combine the d's. You don't have to show every step here. And I'm going to subtract 0.25 from both sides of the equation. And we get 3.95. So now I'm going to take these two equations and put them together in a system of equations. And so I have this equation down here, and I have this equation here. And I'm going to solve that system, and I'm going to use elimination because there's no variable that's solved for in these equations. So I'm going to multiply both sides of the bottom equation by 0.05. There's a lot of different ways you can do it. So I'm just going to rewrite the top equation because I'm not going to change that equation. And by the way, you're going to be able to do this a lot faster because you're not going to have to explain it to anybody. You're just going to be able to do it. So if I multiply the bottom equation by 0.05, then I get I get 0.1d plus 0.05n. And don't be afraid to use your calculator. That's completely fine to use your calculator. So 29 times 0.05 is 1.45. And the reason that this is beneficial is because now we can subtract the bottom equation from the top equation, and these cancel out. You can also multiply both sides of the orange equation by negative 0.05 and then add the equations together. Either way is fine. So I'm going to subtract these, and I get 0.25d. And if I subtract the n's, obviously they cancel out. And if I subtract these, I get 2.5. And then if I divide both sides of the equation by 0.25, I get 10. So there are 10 dimes. So that is one of my answers. So now I can backtrack. I can now take this orange equation along with my number of dimes, and I can figure out the number of nickels. So 2 times 10, that's the number we just found, plus the number of nickels is equal to the number of well, just equal to 29, so we get 20, and subtract, and we get 9, so there are 9 nickels. So now we need to figure out the number of quarters. So to do that, we have to go back, and we could just use the yellow equation. That would be very easy to use the yellow equation. So the number of quarters plus 1 is equal to, actually 1 is on the other side of the equation. Number of quarters is equal to 1 plus the number of dimes. So I'm going to make that yellow. So you don't have to use these colors. You want to try to show the reader what you're doing as best as you can, but it's kind of hard to draw an arrow from there, so you don't really have to do that. So we know the number of dimes is 10, and therefore the number of quarters is equal to 11. So that is the end of that problem. So that was the test. If you got that answer right on number 25, good job. So that was the class today. If you want to take screenshots of this test to help you with the practice test for homework, go ahead and do that now. Here's screenshot number 1 and screenshot number 2 and screenshot number 3 and number 4 and number 5 and number 6 and number 7. But don't go before you get your practice test for homework. The homework is another practice test. So here's screenshot number 1 of the practice test, and number 2, and number 3, and number 4, and number 5, and number 6, and number 7. But don't go before you get the answers. Remember, it's not enough just to attempt the homework. You have to do it completely and correctly. So here's the answers. Screenshot number 1 of the answers. And screenshot number 2. And number 3. And number 4. So be sure to get that practice test done for homework. Remember, don't take the test in the next class unless you first finish the practice test for homework. And be sure that you finish the practice test, or that you attempted the problems that we did together just now. So I'll look forward to seeing you in the next class.